In this problem we have a mass of 4 kilograms attached at one end of an elastic string of natural or original length of 900 millimeters. The other end of the elastic string is fixed in position at this point here. The 4 kilogram mass will rotate to create a horizontal circle about O of radius 600 millimeters. When the string has completed one circle, it will have traced out in effect the curved surface of a cone. So this type of question is known as a conical pendulum type question. For this question, the modulus of elasticity of the string and the angular velocity of the mass need to be calculated exactly in terms of g. The first thing to do in this type of problem is to put onto the diagram all the relevant forces. First of all, put the tension in the string acting upwards as shown by this arrow, and then resolve this tension into a horizontal component which will be T cos y. I have let the angle of the string to the horizontal be y. It is cos y because we have the adjacent and the hypotenuse, and the vertical component of T is given by T sin y. Sin y because we have the opposite and the hypotenuse. T cos y will actually produce the centripetal force towards O. There is also the weight of the 4 kilogram mass acting vertically downwards with a magnitude of 4g. Because the answers are required in terms of g, we cannot just work angle y out in degrees, so we will need to find sine y and cos y as fractions. First of all, the actual length of the string will need to be calculated. So by using Pythagoras' theorem, the actual length of the string will be the square root of the radius squared plus the height squared, which will give the actual length of the string as being 1 meter. Now for sine y, that will be given by the opposite 0.8 divided by the hypotenuse, which is 1. As a fraction, that will be 4/5, and for cos y, that will be the adjacent 0.6 divided by the hypotenuse 1, which will give as a fraction 3/5. Resolving vertically, this is a double arrow because the 4 kilogram mass is only moving horizontally and not vertically up or down. The vertical force that is acting upwards is T sin y, and the vertical force acting downwards is 4g. So rearranging this equation, T equals 4g over sine y. Replacing sine y by 4/5 gives the tension in the string in terms of g as 5g newtons. Now for an elastic string, the tension equals lambda x over L, where lambda is the modulus of elasticity of the string, x is the extension, and L is the natural or original length. So rearranging this equation, lambda equals TL all over x. Substituting the tension as 5G and the length as 0.9 meters, that's the original or natural length, then the extension will be the actual length of 1 meter. Take away the natural length, which is 0.9, gives an extension of 0.1 meters. Dividing 0.9 by 0.1 gives 9, and 9 5s are 45. So the actual modulus of elasticity of the string is 45 G-newtons. Now resolving horizontally towards the centre, the force towards the centre is T cos Y, and this produces the centripetal force. Now the centripetal force is given by mr omega squared, where omega is the angular velocity. As I have said here, mr omega squared is the centripetal force, and r is the radius of the circular path in meters. Rearranging this equation, omega squared equals T cos Y all over mr. So T is 5G, cos Y is 3/5, the mass is 4 kilograms. Now the radius is 0.6 meters, which as a fraction is 3/5. So this 3/5 cancels with this 3/5 to give omega squared as 5 over 4G. To go from omega squared to omega, you need to square root. So we need to square root the right hand side as well, which gives the square root of 5G over 4. I have split this up into root 5G divided by root 4, which gives a half root 5G radians per second as the answer.